As we recall, linear regression is not robust against outliers. If we have an outlier in our data, it can result in a bias of the linear regression model, even when the model assumptions are satisfied. If we remember from last time, the assumptions are that the errors are normally distributed with a mean of 0 and the same variance, and the x's are fixed, they're not measured with error. And the errors are also independent. And we have a linear model. So that's just a little quick review of what we learned last time. Today we're going to go over some methods that have been developed for detecting outliers and removing them if necessary. But most of the time we want to keep them in our data or do two separate models to see what would happen if we excluded it or included it. But I'll go over that in a little bit more detail in a few slides. So here's a little comic I found. So this is an example of why you might want to keep your outliers in your data, because it might give you information that you wouldn't have had if you excluded it. Yeah, it's a little weird. Okay. So if we recall from before, outliers are data points that fall outside the overall data distribution, and they might have be more extreme in the x direction or more extreme in the y direction, or they might fall somewhere in the normal x. I shouldn't say normal because then they'll think normal distribution, but somewhere in the range that we would expect for x and y, but the data point itself is very extreme. I'll show you that on the next slide. So that's different than an influential observation. An influential observation is a data point that greatly changes the regression line if removed. So outliers are not necessarily influential, but they can be, and they can greatly impact our regression model. And influential observations are not necessarily outliers. So that's something to keep in mind when we're going through this analysis of outliers and influential observations. Here are some examples of outliers. In the first picture there, example 1, you can see that this point is an outlier with respect to x, because the x value is a lot greater than the other x values that we have in our data, but the y is an extreme. It falls in the range between 0 and 10 that the rest of the data does. In example 2, we have an outlier with respect to y. We can see that it is much greater than the range of the other data. So it's about 20 when the other ones are between 0 and 10. But the x value isn't an outlier. We look at the other x's that were collected, it's between 0 and 20, and this value is 10. So just another example of an outlier. And then example 3, it's an outlier with respect to x and y, and you can see that from the plot there. We can also have outliers that aren't extreme in either x or y, but the point is farther from the distribution than we would expect. So you can see that it falls much great above the line there of the plotted points. And if we have outliers in our data, they can be influential and can skew the line of our regression model, but they might not. So in the first example, we have an outlier, so it has a much greater value of x and y than the rest of the data points, but it's not influential because the regression model, it's not much different than the regression model. But in the bottom example here, we can see that this point is an outlier and influential. The red line is what would happen if we included that outlier in the data. So it greatly changes the slope of the line and greatly changes our regression model. So if we would have included that outlier in the data, it might not give us an accurate representation of the relationship between our x's and y's. But it might actually be a true data point. So we might want to do two different graphs, two different regression models to see what would happen if we included it or excluded it. If we have an outlier with respect to y and not to x, as we can see in this plot here, it may not be influential. We can see that this red line, the slope of the red line doesn't really change if we include that point. The only thing that really changes is the intercept. So it doesn't make a big difference in our regression model. On the other hand, if we have an outlier with respect to x, even if it's only a mild outlier, we can see it's not much different than what would be expected off the line for the regression model. But it skews the line a lot by including that outlier point. And if we have an outlier with respect to x where the outlier is much greater than we would expect, so this is you can see this point here, it can be enormously influential. So the y line, the red line, you can see how the relationship between the x's and y's is a lot different than if we would have excluded that data point. So some conclusions from the plots that were shown previously. If x is an outlier with the distribution to x, then xy is likely to be influential, even if it isn't an outlier with respect to x and y. So when we have x's that are extreme, they're more likely to be influential than just if the y is an outlier. But if y is an outlier with respect to the distribution of x and y, then xy is likely to be influential. And this is particularly if x is also an outlier with respect to the distribution of x. So x is the really important, influential, very influential in our model. And if we have only one predictor variable, identifying these outliers with respect to x is easy. We can just look at the plot like we did in the previous slide. We can use box plots or other techniques that we've gone over before. But if we have more than one predictor, it becomes a lot trickier. Here we have two predictors. So we have looking at the outliers in a two-dimensional distribution. It's still possible just by graphing. So you can see this red point here. The problem comes if we have many predictors, because I can't see things in 5 dimensions by plotting them. So then we have to use some detection methods that we'll go over next. And even if even if none of the individual xi's are outliers, it might be an outlier itself. So even if the values, so let's say we have 3 predictors like we did in the stack loss model. We have airflow, water temperature, and acid concentration. Even if those values fall within the range of the other data points, they might be extreme, like we saw with the outliers with respect to, that weren't with respect to x or y. So it might just be different from the line than we expect. So that's very hard to see. Even if you were to take each predictor and make a box plot for each predictor, you wouldn't even identify that. So we're going to go over some techniques that we can use to identify outliers. The 4 detection methods that we're going to go over today are leverage, which is the hat statistic, DF beta, DF fit, and Cook's D. And all of these give us different information about whether the points are influential, and we can make conclusions from looking at all of these together. So the leverage of an individual observation measures the potential for influence resulting from an unusual X value. So in multiple regression, leverage reflects how unusual the combination of X values is. So this might actually be a data point that falls right on the distribution line that we'd expect, but it's a lot more extreme than all the other data points we've collected. The most common measure of leverage is the hat statistic, which is represented here by H subscript I. So I is the observation. And I wish I had a cool story for why it's called the hat statistic. It's because you use Y hat as an estimator, and so it's more complicated regression stuff. But I always picture a little hat when I see it because I've seen this a lot of times. It uses the hat matrix, and Dr. Barrett told me a story about how when his wife heard about it, she pictured like Matrix the movie and running through a bunch of hats and a maze. So yeah, sometimes when you do a lot of statistics, your mind kind of goes in funny places. So the formula for the hat statistic is complicated, but R calculates this for us, so we don't have to deal with all of that computation. So HI ranges between 1 over n and 1. So greater values of H indicate that there could be a concern. So if we have a hat statistic greater than 0.2, it's cause for concern, and a leverage value greater than 0.5 should generally be avoided. So those are just some rules of thumb to keep in mind when looking over your data points. So the leverage only measures whether a particular combination of X's is unusual. It doesn't even look at the value of Y. So even if we have an observation with a high hat statistic, high leverage, it may not be influential if the true value of Y is very close to the value of Y predicted by the model. So here we want to plot the residuals versus leverage for each observation. That gives us a lot more information about if it's unusual and influential. And if we have an observation with high leverage and a large residual, it's likely to be influential. I'll go over how to plot that in a few slides. The next diagnostic technique we have for identifying influential observations is DF beta and DF fit. They directly measure the effects of the model when we delete the observation of interest. DF beta measures the effect of deleting the ith observation on the estimated coefficients. And if we remember the coefficients, those are the beta terms, so that's the difference in beta. So if we were to take out one observation, how much would that affect the relationship between each predictor and the outcome? DF fit is the difference in fit, and that measures the effect of deleting the ith observation on the predicted values of Y. So both of those give us information about how the model would change, but we have to look at both DF beta and DF fit to see how different it would be. So for a given regression coefficient, beta k or bk here, and observation I, DF beta ki is defined to be the amount that beta k changes when the observation I is deleted. So if we go back to that stack loss model where we had the three predictors, airflow, water temperature, and acid concentration. So if we considered airflow to be our first predictor, then DF beta 1,1 would be how much the coefficient on airflow would change if we removed the first observation. So DF beta is measured in standardized units. So if we had a DF beta Ki of 0.3, it means that the coefficient on that predictor K increases by 0.3 standard deviations when the observation is deleted. So a greater value of DF beta indicates that it would, if we removed that individual from our regression, that means it would shouldn't use significant because that's a statistic term, but it would greatly change the model. DF fit is defined to be the amount that the predicted value of y changes when an observation I is deleted. So once again, it's measured in standardized units. So do we have any questions on the hat statistic or DF beta and DF fit before I go on to another tool we have? Yes. So for the leverage, it will tell you how extreme those x values are. And for the DF fit and DF beta, it tells you how the model would change if you were to remove that data point. Does that make sense? I'll go through, after I go over Cook's D, I'll go over how we can interpret all these values. So Cook's D measures the influence of the ith observation on the model as a whole, rather than a specific coefficient or predictive value. So this kind of gives us information about, it's like combining DF beta and DF fit in a certain way. So DI reflects the ith case influence on all the coefficients and all the predicted values of y. So in general, if DI is greater than 0.5, then the observation is worth examining more closely. And if it's greater for 1, that's cause for alarm. So it has a huge impact if it's greater than 1. And if it isn't a true data point, then we're getting a lot of, our model could be very wrong. So just because an observation is influential doesn't mean that it should be deleted. So if an influential observation represents valid data, then excluding it may bias our results. It could be that we're not using the right model to predict those values. We could have, it might not be a linear relationship, and we just don't have enough data points out at those extreme values to show that relationship correctly. So we must use caution and common sense when deciding what to do with influential observations. So if the observation is physically impossible, so if we're measuring weight of adults and we have a value of 2, that's not really possible. But if we have a value of 300, if we're looking at pounds, that's possible. It's just extreme value. So we'd want to only remove data points if they are results of measurement error or if they're not representative of the population. If we're unsure, we can report both with and without that influential observation. So that's being safe. We could do 2 regression models. If possible, it may help to collect more data points that are similar to the observation in question. So if we have a very extreme value in X, so if we're looking at weight as a predictor of some health outcome, we could collect a lot more data points on individuals that had more extreme weights, and that might give us a better, more information about the true association between that predictor and our outcome, to see if it is linear, see if all of the assumptions that we talked about last week hold for our model. So the test statistics we've described previously are useful tools to identify influential observations, but they aren't foolproof. So here it comes down to a judgment call by looking at all of this information. So we have to use common sense in addition to these statistics. Rarely is there an obvious right answer. So we can have R calculate all of these statistics for us. So here, the R command is influence measures, and we can see that this stackloss.lm, that's the regression model that we created previously. So here we input that regression model into the command influence measures, and it returns all of these statistics that we've talked about. So this is, if we remember, for stack loss, the predictors are airflow, water temperature, and acid concentration. So the DFB.1, that's the impact of removing each of these observations on the intercept. So if we were to remove observation 1, it would cause the intercept to decrease a little bit. DFB.AR.F, that's the how much the coefficient on airflow would change if we were to remove the specific observation. And remember that it's in terms of the standard deviation of the coefficients. So if we have, I think the general rule of thumb is 2, so 2 standard deviations different means that it has it's very influential on those coefficients. So if we had a lot of time, we could go through all of this and see the points that are most influential for the DF betas. These little stars on the side tell us which points. It kind of summarizes what's going on in the data to tell us which points are most influential. The DF fit tells us how much the Y's would change, the predicted Y's would change if we were to move those observations. And then Cook's D gives us information about the total model, so how the betas would change and the predicted Y values would change if we were to move those values. The hat statistic is that leverage, so it tells us how extreme the values are in terms of X. And then this influence on the far right that highlights the points of interest. So it tells us that observations 17 and 21 are observations that we should look at more to see how much they influence our point and if they are linear regression model, and if they could be outliers. So are there any questions on this? It's a lot of information on one slide. Okay. So we'll go through then. So some notes on what this R command does is it returns a list of influence measures for each observation in the model. This is the DF beta, DF fit, Cook's D, and the hat statistic. So once we have that information, we want to plot the residuals of a regression model against the leverage of each observation to see how those, if values are extreme, how they influence the model. So it might be that we have an extreme value for X, but it falls right on that regression line, so it doesn't have a lot of influence in our model. So here we use the plot command that we learned about last time, and we don't specify which. We just want all of the plots that it gives us. So it gives us the QQ plot and the plot of the regression versus predicted Y, and then this plot of the residuals against leverage. Okay. So here's the leverage plot for the stack loss data. So if we have the standardized residuals on the y-axis, the leverage on the x. So what we're trying to find is we're trying to identify observations that have extreme residual and extreme leverage. So if we have values. So we want to look at both the top part and the bottom part of the graph because it could be extreme positive or extreme negative for the residuals. And then we want to look at the leverage. That, remember, at 0.2 is we want to look and see if there's any greater than that. These dashed red lines are the Cook's distance. So that gives us some information about how it would affect our model if we were to, how influential those points are in our model. So if they have a value greater than 0.5, those points are very extreme and very influential in our model. So we can see that only observation 21 falls into that cutoff region. Observation 17 was the other observation that are identified as being a potential problem. That doesn't even show up here because the residual is very close to 0. So the predicted y is very close to the actual value for y that we got. So it's not very influential. So if we identified that observation 21 is highly influential. We may want to refit the model excluding observation 21 just to see how it would change. Observation 17 has high leverage, but it doesn't appear to be influential. So it just has an extreme value for x, but it's not different from the model that we predicted. So how we can remove observation 21 is we can just do a subset in this regression command here. So we have we identify the data, the predictor, and then we identify the outcome in our regression model, and then the predictors, and identify the data as static loss, and then subset minus 21. So that removes observation 21. And then the summary gives us all of the coefficients and other information of interest about our regression model. So you might want to keep this slide up if you have or I could just write it up on the board. So we'll look at the residual standard error as 2.568, and our R squared is 0.9392. I'm going to show you in a few slides what would happen if we kept 21 in, so I'll just keep a few of those statistics on the board to see how it changes. So if we remember, LM is our linear regression model. If we insert this subset in the parentheses there, if we have a minus I, it removes the ith observation. Or we could just do subset 1 to 20, so that only includes those observations numbered 1 through 20. If we go back to the regression including 21, we can see that our error is a lot greater if we keep that observation, and our R squared is smaller. So the model doesn't fit the data as closely. We also have some change in the coefficients and the relationship between those predictors and the outcome. So removing observation 21 results in an increase in R squared and a decrease in the residual standard error. There's also a decrease in the coefficient for water temperature. If there's a reason to believe that observation 21 is not representative of the population, or if it's just an error in measurement that we're sure about, then there's a strong case for removing it. Otherwise, we should retain it or report both versions of the model. And to be safe, reporting both versions of the model is probably what we want to do here, because if we were to delete that observation, we get a regression model that much closely fits the data, but if it's a true data point, we want to keep it in there too. So by showing both of those models, it gives both of that information. So some points to remember from the lecture today. Outliers and influential observations can have a large influence on a regression line. And there are various statistics for identifying influential observations. These are the HAT statistic, which is the leverage, DF beta, DF fit, and Cook's D are the main ones we want to look at there. And when an influential observation is identified, we need to use common sense to decide what to do with it. So are there any questions? Nope. Okay. And then the R commands that we learned today are the influence measure commands, which returns a list of the influence measures for each observation in the model. So we can look at that to identify which observations have the greatest influence or are the most extreme in our model. Then we can use a plot of the regression, the linear model, to return a leverage versus residual plot. Actually, I think it's residual versus leverage. So we can identify which observations are most influential and most extreme. And then we can subset out the data points that we've identified to be a possible problem by using this subset in our LM command to regress Y on X using only the data in the subset. And we can do a minus a value if we just want to exclude one value. So using all of these R commands saves us a lot of time, and it helps us to identify which observations we should keep. So I'll end there.